Okay, with this example of the ideal gas law, it says if 1 liter of fluorine gas measured at 22 degrees Celsius at 0.95 atmospheres of pressure reacts, how many grams of potassium fluoride will be produced? So we're working this one kind of in the reverse of what we did the previous ones because we were given grams before. So what I need to do is with my ideal gas law, once again, it was PV equals nRT. I'm going to need to solve for N. So when I solve for N, I divide both sides by RT, correct? So when my final equation comes out, that's going to cancel. So N is going to be equal to PV over RT. So I'm going to go ahead and solve for N. So I take my pressure, which is 0.95 atm. I take my volume, which is 1 liter, and I divide that by R, which is the constant. My labels, liters times atmospheres all over, mole times Kelvin. And finally, my temperature. I need to convert my temperature into Kelvin once again. So I add 273.15. So that's what? 295.15? Sound right? 295.15 Kelvin. I do my math now. So as I do my math, I come up with 0.03924, and my label should be moles when I get, here's an atoms or atmosphere cancel, here's a liter cancel here, so I have an inverse, bring it up here. I have moles, but I have moles of what? I have moles here, but I have moles of what? Fluorine gas, right? So I have moles of fluorine gas. Now I'm going to take that moles of fluorine gas and I'm going to just round it to there, but I'm going to leave that whole big number in my calculator. I'm going to take that mole of fluorine, and my final answer I want to be in grams of potassium fluoride. So I'm going to use my balanced equation once again and convert that into grams of potassium fluoride. Have to find my molar mass of potassium fluoride. And I came up with a value of a molar mass of 58.0967 grams. So I get my cancellation there. I get a cancellation there. I am going to have my final label is grams of potassium fluoride. So when I do the math, I come up with 4 and I look at sig figs, I see 2, so I have 4.6 grams of KF. We thumbs up with these problems here? Okay. Because this one's a little bit different. This next one, just a teeny bit. So I'm going to give you a second here to copy this, the wording of this problem down, and then we'll work it. Now this example is a little bit different. Okay, it says when 8.0 liters of oxygen gas at 0.98 atmospheres of pressure and 25 degrees Celsius are reacted with sugar as shown, what volume of carbon dioxide is produced at 37 degrees Celsius and 98 atmospheres of pressure? So we have 2 different sets of data here. And we are going to use PV equals nRT twice. All right? So what I am going to do to start with is I'm going to take the PV equals nRT and convert it to moles of oxygen gas. So just like we did in the previous example, PV equals nRT. So I know that N is equal to, PV over RT. By manipulating my equation. So when I do so, pressure times volume divided by the constant times the temperature. So this is at 25. So that's going to be 298.15 Kelvin. Do my cancellations. I indeed am going to come up with a mole as my label. So when I do my math, I come up with 3. Check. I come up with 0.320286, and this is moles of oxygen, right? We okay thus far? Now, I'm going to take my moles of oxygen and convert that into moles of carbon dioxide. So I need to have the molar ratio from the balanced equation. So I'm going to take the 0.320 mole of oxygen. Just going to be a one-stepper. So I know that 6 mole of oxygen, 6 mole of carbon dioxide. Go ahead and take a break. Okay, we'll finish this when you get back from break. All right, getting back to this problem. Would we agree that multiplying by 6 and dividing by 6 is going to give us the same number? So, I have now converted this into moles of carbon dioxide. Now, my problem wanted to know what volume of carbon dioxide is produced at 37 degrees Celsius and 0.98 atmosphere pressure. So, all we have done here, folks, all we have done is we had that reaction occur, then we increased the temperature. Did we increase the pressure? Pressure stayed the same, didn't it? So we increased the temperature. So what I'm going to do, I'm going to get rid of this stuff, but I keep the mental of the 0.3, whoa, okay, the 0.320, but I need to solve for volume now. So by working my equation, I divide both sides by P. So my volume is going to be nRT over P. Well, N was 0.320 mole carbon dioxide. R is the gas constant. T is my new temperature. I divided both sides by P. Okay? It was PV equals nRT. So now I need to take that pressure, put that pressure on the bottom. So I've got an atmosphere canceling, I've got a Kelvin canceling, I've got mole canceling. It's leaving me here with liters. So my final answer is going to be in liters, which my volume should be. I look back, I'm going to have 2 significant figures. So when I do my math, I forgot to put that 821 in there. When I do my math, I come up with 8.3 liters. Sound right? So I had to use my ideal gas law, my PV equals nRT, twice for that particular problem. Okay, now let's look a little bit about some before and after calculations. So you're going to need to get this into your notes also. Let me move my little recording box so we can see that a little bit better. And I'll give you a second to copy this down, and then we'll talk about it. So we're looking at this, and we're going to call these before and after calculations. On these before and after calculations, we will know 4 variables, and we will be asked to determine 1 variable after we rework the conditions. So we could change one thing, we could change a couple of things. Okay? So it'd be somewhat similar to that last problem we did. We could find out what something was and then, for instance, increase the temperature and see how that affected the whole equation. So the big thing we need to know is this equation right here, where P1V1 over N1T1 is the initial, the 1. That means it's the first. That's what we started with. And the final one is going to be the 2. So P1V1 over N1T1 is equal to P2V2 over N2T2. All we're doing is just reworking the equation. So if I have this question right here, we can go ahead and calculate that. So here is our before and after problem. Get that in your notes, and we will work it. The problem states that argon is an inert gas used in light bulbs to retard the vaporization of the filament. A certain light bulb containing argon at 1.20 atmospheres and 18 degrees Celsius is heated to 85 degrees Celsius at a constant volume. What is the final pressure of argon in the light bulb? And they want that in atmospheres. So when I read that question there, okay, it says that it is at a constant volume. So does my volume change from before to after? No. Okay? Do the amount of moles in this light bulb over here, okay, do the amount of moles in that light bulb right there change from before to after? No. All right? So, my clicker's not working. So, N and V are constants, so they can be left out of the equation. Why can I leave them out? They're the same on both sides. Okay, they're the same on both sides. So if I leave them out of the equation, I now have the equation of P1 over T1 equals P2 over T2. So all I've done here, folks, is just taken the V and the N out. So there's my new equation. Can I take P1 over T1, P2 over T2? Using that data? Absolutely. And I work my equation, in order to solve for P2, so P2 is going to be equal to P1 times T2 all over T1. When I do the math, I'm going to come up with 1.48 atmosphere of pressure. But I even have this wrong in my notes because that's not sig figged, is it? What should I have? I should have 1.5 because I only have 2 sig figs for my temperature up at the top. So I'll have to change my notes here. So you might run into some before and some after problems on your WebAssign. Yeah, Garrett?
So how did you get like T2 over T1 like that?
Like that? I mean, really? Okay, I could have wrote it like this, Garrett, when I'm going. He's asking why do I have it like this right here? Okay, I could have just simply done this. So I could have had P2 is equal to P1 T2 over T1. That's the same thing. All right? I could have just done it like that. You're going to get the same answer when you multiply them and divide them out. Okay? Gas density. We know that density is equal to m over v. So I'm going to give you a new equation here. Okay, so I'm going to give you a new equation here. And how this is going to work is that all this stuff, folks, is just showing you how, okay? Just showing you how I'm going to work this in order to find the density, okay? So I'm not real concerned with you knowing how I came at this. I'm just showing you how that all this stuff canceled to give me grams per liter there. The big thing is right up here that this M, this capital M, is the molar mass of the gas. Okay? The molar mass of the gas in grams per mole. So when we do this, and I get this to come out, I have my final label as grams per liter, which is a density. So we can find the molar mass of this substance by reworking this equation and solving for M. And when I do so, I see that M is equal to d RT over P. My density is grams per liter. There my liters will cancel. Okay. I see that I have atmosphere canceling. I see kelvins canceling. So that'll leave me with grams, moles. Okay, and like I said, I'm just walking you through this. It's not important for you to know the, all of these inner workings here. What's important is that you know this here, folks. Memorize this equation. Okay? Now I'm going to show you how I memorize this equation, because I take and I get the P right here. I multiply both sides by P so I don't have anything in the denominator. So PM equals dRT. This is the equation to do the density calculations. Now, how do I remember PM equals dRT? When you are post-mortem. Okay, what's that mean? All right. When you're post-mortem, you're covered with dirt. That's how I remember it. PM equals dRT. Post-mortem, dirt. So PM equals dRT. Let's do a gas problem here then. Let's do a gas problem. Give you a second to copy it. A 2.10 liter vessel contains 4.65 grams of a gas at 1 atmosphere pressure, 27 degrees Celsius. What is the molar mass of the gas? I know PM equals dirt. What am I trying to solve for here? Molar mass, which is what? M. So I'm trying to solve for M. So if I divide P by both sides, I can get M by itself, right? So M is equal to dRT over P. Okay? dRT over P. So I need to get D first, which is what? Density, right? How do I get density? Mass divided by volume. So let me do it in a different color here, because my density is going to be 4.65 grams over 2.10 liters. So my density is going to be 2.21 grams per liter, because that's my density. My R is still my gas constant, And my temperature is going to be 27 times 273.15. So that's going to give me 300.15 Kelvin. My pressure for this whole thing is 1 atmosphere. So let's go through and let's look. When I do my cancellations, okay, I have a liter here. I have a liter here to cancel. I have atmospheres canceling. I have kelvins canceling. So what's my final label going to be? G over M, grams per mole, which will give me a molar mass. So when I do my math, I come up with a value. How many significant figures? 1, 2, 3, 1, 2, 3 significant figures. So my molar mass is going to be equal to 54.6. Grams per mole. So this is just a little bit different of an equation than the ideal gas law, the PV equals nRT. This is the density one, which is PM equals dirt. Naira, you have a question? Okay, did you use the whole drawn out thing for the ideal gas law? 0.082. Okay, see, I rounded it. It's going to be a little different if you round your ideal, your constant. I'm okay with you using 0.0821. It probably wouldn't hurt. Isn't that what we just talked about? That's what you were talking about, right, Anira? Okay, did you round this right here? Okay. Did you use 2.21 or did you use the big long number that we got for the volume? Huh? Okay, I used the big long number. Okay. Yeah, Garrett?
I didn't round the 0.0821 until I didn't round anything to the end, and it was right. So
Don't round it till the end? Okay.
well, 0.0821.
Okay. That's okay. All right. Garrett said it on WebAssign it's okay to round the ideal gas law to the 0.0821. He came out with the correct answers there. Now, we've got one final thing yet to do here, people. And it's called Dalton's Law of Partial Pressures. And you can see here that there's a lab going on where they're bubbling a gas and displacing that water and collecting that gas. We will do a lab on this later on. And I'm talking, I've already got next week planned out, so it won't be next week. Okay, you'll take your test over stoichiometry next week. All right, but we'll do this lab afterwards. So, you're going to need this Dalton's Law of Partial Pressures when we do that here after the semester exams. So, Mixtures of gases require special handling when doing calculations. Now, the reason being, as you can see up here, I have my gas here, but I have evaporated water particles in my gas. So not only is this the pink gas that I have collected, I have water evaporated in that gas. So I have to take that into account, that this pink solution that I'm collecting here, this pink gas, is not just the gas. So the total pressure is going to be equal to the pressure of the pink gas and the pressure of the water vapor. Well, it'll be some sort of a gas, yes, and it'll be water vapor, okay? So the pressure of the water, the pressure of the gas, that's what the pink and the blue is there, okay? Can you see, though, why we called it Dalton's partial pressures? Because part of it's water and part of it's the gas. So here's an equation that we're actually doing here. Here's an experiment. All right? You probably did this in IPS. Yeah. All right? But we have a test tube up here that has sodium chlorate in it. You heat that, and based on our reaction predictions, we know that the following equation here happens. Okay, sodium chlorate, when heated, decomposes to sodium chloride and oxygen. So what is the gas I'm collecting? Oxygen. So here's a whole bottle of gas that I've collected that is oxygen. But is it only oxygen? No, because of what? It's got water vapor in there too. Okay? So that bottle has oxygen gas and water vapor in it. So my total pressure is going to be the pressure of the oxygen gas and the pressure of the water vapor. So PT equals P sub O2 plus P H2O sub. So if I take the partial pressure of water and the partial pressure of oxygen, I get the total pressure. Make sense so far? Now, when I go through this, Dalton's laws of partial pressure. P1, P2. Okay, so that's my total right there. Okay, my partial pressures. This is just another way of showing you what I just had in that, the total pressure, okay, with the oxygen and the water. Okay, because if you look at this, okay, did we increase the volume in that container? No. Did the temperature increase? No. Okay, so those are constant. That's why we can take the P1 plus P2 is equal to the total pressure. Now, this right here, this slide is just showing you the partial pressure of water. So if you look at this, by reading this chart, or I could use this graph, by reading this chart, I can tell you what the water pressure is. when you do this lab later on, I'm going to actually give you a chart that you'll have to read to determine the water pressure. But what is the pressure of water vapor at 15 degrees Celsius? 12.79 millimeters of mercury. What's the pressure of water at 80 degrees Celsius? Water vapor, I should say. 355.1 millimeters of mercury. Okay? So if I can read a chart, I can determine the water pressure. So, if I manipulate my equation, my total pressure, right here, my total pressure minus, minus my vapor pressure of water will give me the pressure of the gas. Does that make sense? So if I were going back to the water and the oxygen that I had before, this right here, gas collected, that would be the PO2. Now, can I determine the total pressure right now in this room? Could I? I could use a barometer. What we will do, okay, we're going to, when we do this in lab, we're going to just take the pressure that we have on for Salina, okay? So what we'll do when we do this lab later on is we're going to take the air pressure that we have in Salina, and we'll get that. I'll show you how to do that. We'll get that off of the Weather Channel later, okay? But I just wanted to show you this partial pressures, and hopefully you took good notes on that because you're going to need that for that lab in a couple of weeks, okay? Now, that's all I have for you today.